hopefully we'll cover SIMD processing, single instruction, multiple data. We'll get into GPUs a little bit, how they are actually examples of SIMD machines, and hopefully we'll get to VLIW. And next week we'll start with the memory system, for which you've done readings, hopefully. Okay, reminder, you know that the homework file is due April 2nd, and hopefully you know this by now. And work on the extra credit, it's a lot of fun. Okay, lab assignment 5 will be out today or tomorrow, but 3 things that I would like you not to forget: turning your feedback sheet by the end of the weekend, and for your convenience, I copied the thing you can click on and go to the feedback sheet, or you can copy and paste also. Attend the discussion sessions this week and the next, because they will be important. TAs will go over the exam solutions, which are already up, and for Lab 5, TAs will describe the timing simulator, so you can ease your job quite a bit if you go to discussion sessions, because you will be given this timing simulator. You will be required to understand how it works, and if someone else describes you the high-level structure and what's happening in the code, it's a lot easier to understand someone else's code. So this will be very beneficial for you. Otherwise, you'll have to figure it out all on your own. Okay? There is documentation in the code. Chris wrote the simulator, but it's a lot easier if you actually go to the sessions and the TAs can tell you. Pick up your exams and homework at the end of class today. And remind me to end the class a little bit early so that we can distribute these things. I don't know if that'll happen, but just remind me. Okay. First, I would like to distribute these prizes for the top 3. Top 4 got the extra credit, but I left the prize at 5.5%. Hopefully, Jonathan will get it in the next lab, the prize. 5% is a big difference, big performance difference, actually, in real systems. Companies like Intel and AMD fight with each other to get 5% better performance. So, I'll give you the first book to read. Where are you? You're far. You make my life harder. Okay. Well, these are all reference books. Jason? Oh, you're here. Right here. Okay. I'm not looking around. And Tyler. Sorry. This last book is the Pentium Chronicles. It's a good book. It's by the chief architect of Pentium Pro, Bob Colwell. The first book was The Structure of Scientific Revolutions. It's a more philosophy of science book. It's not really a computer book, but hopefully that'll be inspiring to you. I don't know if you're into that kind of books. Maybe you will be after this. Okay? And the second was The Soul of a New Machine that you saw last time. Okay. So if you want books, do the extra credit. Or just for fun with it. Okay, reading for next time. Actually, I will add one more reading, but that'll be later. Okay, last time we wrapped up automotive execution. We covered memory disambiguation in some depth. And we also talked about different design choices and combining concepts. So please go over the lecture, understand what memory disambiguation is. If this term is totally unfamiliar, maybe you were sleeping in the lecture, or you forgot what it is, but you should know what it is. We covered data flow graphs, the concept of exploiting irregular parallelism. Data flow machines are the most powerful machines in exploiting irregular, fine-grained parallelism, finding independent instructions from any different place in the code. And the code is in an ISA, data flow ISA, expressed as a data flow graph, if you will. So we covered all of that. And we started vector processing, and we will continue vector processing. So this is some of the most irregular machines that can extract irregular forms of parallelism, and then we jump into very regular forms of parallelism. A single instruction operates on multiple data elements. You want to do the same operation on many data elements at the same time. And we talk about vectors. If you want to add 1 million or billion element vectors at the same time, vector processors are very good at that, because you're doing the addition on 1 billion different elements. You can exploit that parallelism, right? It's very regular. And these things exist in real life, right? If you want to, for example, image processing applications. You have a huge image, and you want to do something to each pixel, right? Or you want to combine two images together, and we will see one example later on. These are very parallel problems, data parallel problems. You do the same operation on multiple elements of data. So today we will cover vector processing and SIMD in general, and VLIW. Okay. I guess I did not go over this slide last time because the flow didn't happen well, but right now the flow is nice. So Mike Flynn in 1966 categorized computers in 4 different ways in terms of how much data an instruction operates on. In a SISD computer, single instruction, single data, a single instruction operates on a single data element. This is what you've kind of seen so far, right? The MIPS ISA is a SISD ISA, SISD model, because you're really operating on single data elements. You're putting 2 data elements together, but it's really scalar, if you will. It's what you're doing is a scalar operation. On the other hand, contrast this with SIMD. Single instruction operates on multiple data elements, right? You say add, and add happens on n different elements at the same time. In a sense, you can specify n operations, all of them the same, with a single instruction. And we will go into a little bit differences here. MISD, this is an odd thing. Multiple instructions operate on a single data element. This doesn't exactly exist, but the closest form is something that we will not cover, a systolic array processor, or a streaming processor, if you will, where you feed the data. It's not the exact form. Feed the data to a processing element, and that transforms the data to something else, passes it to the second processing element, and transforms it to another thing, and passes it to the third. It's not exactly MISD, multiple instructions. So you can think of one instruction, another instruction here in different elements, and the single data coming in here. Single data stream, if you will. And then you have another second operand, if you will. It's not exactly MISD, if you will. But think of it that way. MIMD, this is essentially multiprocessors or multi-threaded processors. Basically, multiple instructions operate on multiple data elements. You can put together multiple SISD processors, and you get multiple instruction streams. Okay? So, SIMD is what we will concern ourselves with. That's, in a sense, one of the most regular forms of parallelism. Okay. I've shown you this slide before. In data parallelism, concurrency arises from performing the same operation on different data elements, different pieces of data. And we've done this before. And we talked about array processor versus vector processor. I want to illustrate this a little bit more. This is, in a sense, purist's distinction between different ways of processing, doing the same operation on multiple data elements, either in time or in space. In array processor, an instruction operates on multiple data elements at the same time. In a vector processor, an instruction operates on multiple data elements in consecutive time steps. So, in a sense, here you're exploiting the parallelism in the data at the same time. Here you're exploiting the parallelism in data to pipeline your operations. So let's take a look at it. Let's say you have this instruction stream where you have a 4-element vector. You're loading it into a vector register. And you want to increment the vector and then multiply it by 2. Looks like that's what's happening here, right? So you want to increment each of the elements by 1. That's what this vector add does. And you want to multiply all of the elements after they're incremented by 2. And you want to store the vector back into its place. An array processor has 4 processing elements. Each of the processing elements can do all of the operations. So in the first cycle, you do the load on 4 of the processing elements. You load the 0th element, first element, second element, third element. Next cycle, you do the add. Next cycle, you do the multiply on each element. And these are dependent on each other, right? And we will see how this actually happens. And then next cycle, you do the store. Okay. So you can actually do all of this in 4 cycles, right? Assuming each unit's latency is 1 cycle. In a vector processor, you're pipelining the operation. In the first cycle, you start the load for the 0th element, do the load for the 0th element. In the next cycle, you do the load for the first element and you start the add for the 0th element, because this add is dependent on the load. Right? In the next cycle, you start the load of the second element, add of the first element, and multiply of the 0th element, and so on, if you will. At the steady state, you'll have all of the units filled, and then you finish the loop. So if you look at an array processor, you do the same operation at the same time. This is time going down. If you look at a vector processor, you do different operations at the same time. And if you look at the space, if you will, this is the space where you have your functional units, you do different operations at the same space, at the same processing element in the array processor, but you do the same operation at the same space in the vector processor. Okay? So hopefully you can think of the different trade-offs associated with these two things. Right? In this case, for example, each processing element needs to do all operations, if you will. So this is a purist distinction of people used to build array processors in the early days, and vector processors in the early days. Today's computers are usually a combination of both, actually. Today's SIMD computers, and we will get back to this. You exploit both the data pairs in both space as well as time in a GPU, for example, today. Okay, you've seen this picture. This was VLIW, which we will get to, and this is SIMD array processing. Okay, you've also seen this, but let's cover this again. Basically, many programs use vectors, and we would like to somehow accelerate their processing. What are the requirements in building a vector processor? As we discussed before, you want vector registers, right? There's no reason to have vector registers, but you want to exploit locality within vectors, just like regular registers. A vector processor could operate on vectors in memory. It doesn't need to be a load-store machine, right? But let's build a load-store vector processor. In fact, very early vector processors were memory-to-memory machines. There was no load or stored registers. But registers, as you know very well by now, exploit locality in programs, locality in data. So we would like to have registers. And we would like to provide the vector registers which can store multiple data elements. So you need that. You need to be able to operate on vectors of different lengths. You don't always have vectors of a fixed length. And you don't want to design your machine with a vector that's with something that you can operate on fixed length vectors. So we have a vector length register which the programmer can change dynamically. Well, with code, basically. And the elements of the vector may be stored apart from each other in memory. And we have a way of specifying this, the vector stride register. Remember the picture I put on board last time? Why does this happen? Because you can have a matrix. Well, it can happen due to many reasons, but you can have a matrix that's stored in row major order, if you will. In which case, consecutive elements in the same row are in consecutive memory locations. So the first element is memory location 0, second element at 1, 2, ... Let's say this is 63. And then first element of the second column start from 64, memory location 64. First element of the third column start from memory location 128, ... So if you actually are accessing this matrix in row major order, then your stride is equal to 1, right? You're accessing consecutive elements in memory. But if you're accessing this matrix in column major order, if you want to access the first element, in row 0, column 0, and then the second element, the element in row 1, column 0, and then the next element in the column, and then the next element in the column, then your stride becomes, so if you're actually accessing, if your access is in column major order, then your stride becomes 64. Right? And you can imagine, last time I discussed this, if you're doing a matrix multiply, what's happening is you're accessing this matrix A in row major order, and this matrix B in column major order, because you're taking the dot product of this vector and this vector, which means that your stride in accessing this should be different from your stride in accessing this, unless this is laid out in column major order, right? Okay, you can think about that element. But then what if you want to multiply this with something else as the first element then? Okay. So stride is the distance between two elements of a vector, and you would like to be able to change it. The programmer should be able to change that. Okay. So we've talked about this. Vector instruction performs an operation on each element in consecutive cycles, and vector functional units are pipelined. Each pipeline stage operates on a different data element. And vector instructions allow deep pipelines. Why? Well, because everything's independent, right? In this case, let's say you can do all of the operations, actually all of the operations in the same matrix. Let's say your vector is 1,000 long. You can have 1,000 deep pipeline. And there is no need for dependency checking because all the data elements are independent, right? You're doing add on all the data elements. Yes, there is no need to have hardware interlocking within a vector, no control flow within a vector, and no stride allows prefetching of vectors into cache and memory. So what are the advantages? No dependencies. You can have good pipelining. You can do everything in parallel. And you can do both. And we will see that later when we close the vector processing. We will see that existing processors both pipeline the functional units and have many functional units so that they can exploit this regular structure. Each instruction generates a lot of work. You don't need to fetch. So think about doing a vector addition, and we will see that doing this dot product in a scalar processor. What you need to do is really, you need to fetch the add, well, not add, I guess, multiply. You need to fetch each of these elements, multiply them, and store them, and do all of that for each element. Which means that for each element you need to fetch, I don't know, maybe 5 instructions, let's say. Here, you need to fetch 5 instructions for all the elements. What you're doing is you're amortizing the cost of instruction fetch. Right? So you're amortizing the cost of, I guess, instruction fetch, decode, and bookkeeping, if you will, across many elements, many data elements. Which means that you're saving power also, right? You don't need to fetch the instruction, decode it for every single element. So this is a very power efficient engine as well. You have a highly regular memory access pattern, assuming you're operating on vectors, of course. And we will see how this is a good thing as well as a bad thing because of the parallelism. Right? You have a lot of parallelism, which means that you need to supply the data if you're loading the vector. Whereas if you're fetching from a single instruction, you need to supply only one element, right? But highly regular memory access pattern helps you to actually prefetch data, if you will. And there's no need to explicitly code loops. You can eliminate branches with this, and we will see that as well. Okay. As with everything, there are trade-offs, right? Hopefully, by the end of this course, you will see that there is a positive side to everything as well as a negative side. What is the negative side in case of a vector processor? Say it again?
It needs vectors to operate.
That's right, exactly. If you don't have vectors, in a sense, you're doomed. So, works if parallelism is regular, right? So, vector operations is great. What if you don't have vector operations? What if your parallelism is really irregular? You cannot express your problem this way. For example, searching for a key in a linked list or a tree. That's very difficult to do. In fact, vector processors have scalar units to handle that kind of operations, and those scalar units tend to be the bottleneck of the code. You remember Amdahl's law? You're really bottlenecked by the non-parallelizable or non-vectorizable portion of your code, because that's the part you cannot really accelerate. You can throw more execution units to vector operations, and you can make them faster, but in the end, if you have things like this, they're harder to make faster. So, actually, this is from the paper that introduced very long instruction word architectures as an alternative to vector architectures. What Josh Fisher says is, to program a vector machine, the compiler or handcoder must make the data structures in the code fit nearly exactly the regular structure built into the hardware, which is the vectors. That's hard to do in the first place, and just as hard to change. So if you want to change the hardware, one tweak and the low-level code has to be rewritten by a very smart and dedicated programmer who knows the hardware and often the subtleties of the application area. So you can perhaps appreciate this if you think about it a little bit. And this is a very good paper to read, by the way. I'll get back to that paper at the end. So this is one of the big disadvantages of vector problems. If the problem fits the vectorization well, then it's great. But if your problem doesn't fit well, then you're bottlenecked by that part of your problem. And in fact, we will see when we talk about Cray 1. Cray 1 designers designed the fastest scalar unit in their machine. So it was a big vector processor, but their scalar unit was very fast, so that they're not bottlenecked by these irregular portions of the code. Okay. In fact, actually, let me give you a terminology. And here, this is called the sequential bottleneck, really. And if you look at the operation of a vector machine, if your program is not fully parallelizable, what happens is you have a sequential portion of your code and then a parallel portion of your code where you can I'm looking at these as threads, but many execution units can operate on the data parallel. So this is a parallel, this is sequential. And then you operate on many things. Let's say you finish the matrix multiplication, and then you have a sequential portion of your code again. And then you go into parallel code afterwards. A lot of programs display the structure. A lot of even scientific programs display the structure. And you can make this part faster by increasing the vector length of your machine, right? You can reduce the time you spend in the parallel portion. But now your sequential portion becomes a bottleneck. And this is essentially Amdahl's law. If you read Amdahl's paper, Amdahl was very not optimistic about many programs having a good fraction of this parallel portion, if you will. I'm throwing a lot of terms at you, but you know Amdahl's law already. So Amdahl's law says your speed up is limited by the fraction of your non-parallelizable portion. Right? Okay? So that's why Cray 1 at its time had the fastest scalar unit so that they could get out of these sequential portions very fast with a fast clock. Okay. So another limitation, or this could be a good thing or a bad thing, but a limitation still, because you're doing so many operations at the same time, so many loads at the same time, you would like to supply the data. And usually memory bandwidth can easily become a bottleneck in these machines. And these machines were some of the first machines that stressed the memory bandwidth very heavily. So they had very sophisticated memory systems, which we will get into. Okay, you can think about those. Okay, so let's go into the code or the processing elements in a vector processor. So each vector data register, as I told you before, holds n bits values, if you will. So now you have not a scalar register, but a vector register. This is the vector register 0, and you have elements 0 through n minus 1. Each of them has some width. You have vector control registers. I already told you about vector length and vector scribe. But there's also vector mask, which we will get into. The vector mask register essentially indicates which elements of a vector the instruction should really operate on. And this is essentially branching in a vector machine. Okay? Let's say we don't want to have any branching. Well, this is essentially actually predication in a vector machine. Basically, it's set by vector test instructions. Let's say in this case, this vector test instruction tests each element in a vector register and tests if the element is equal to 0. And you set the vector mask register with true or false, if you will, based on the outcome of that comparison. So let's say your hardware vector length is 64 elements. Each instruction can operate on a maximum 64 elements. You have a vector mask register that has 64 bits, if you will. And these bits can be set by instructions like that. That's a comparison instruction, right? Vector comparison. Each element in the vector is compared to 0, and depending on the comparison, this mask is set. 0, 1, 0, 0, let's say 1. when the 1 is set, that means that the comparison is true. Those elements are 1. Now, when you actually execute the next operation, let's say you do a vector add on this register, on a register, this vector add takes effect only if the mask bit is set. For all the other elements, vector add does do nothing. In a sense, it's a predicated operation. Right? Does that make sense? So this way you can implement branching, and we'll see an example of the code on how to do this. So today's GPUs are actually very similar. The maximum vector length can be n. These are the maximum number of elements stored in a vector register. Okay. So vector functional unit, if you look at a vector functional unit, it takes as input vector registers, it's pipelined, and outputs it result in vector register 3. So 0th element goes in, and then the first element in each vector goes in, second element in each vector goes in, third element in each vector goes in, and they come out. And you feed the registers. And we already said that we use deep pipelines, right? So Cray1 had these vector registers and these scalar registers, and you can read this paper if you're interested. But there are real machines that have been built like this since, I don't know, since the 1960s, actually. It had scalar and vector modes, so it switched between these two different modes. It had 8 64-element vector registers. Each element was 64 bits. And we will see why it wanted 16 memory banks soon. But it also had scalar and address registers to execute the sequential portions of the code. So it had also 16 banks. Why? Let's say you were doing a vector load. What you want to do in a vector load is you want to be able to load each element in consecutive cycles. How can you do this? Well, if you have a single bank memory or single monolithic memory, let's say the memory takes 11 cycles to access. You want to get the first element first. You don't want to wait 11 cycles to get the next element, right? Then you're not exploiting the parallelism. What you can do is you can have 16 ports to this memory, 16 read ports, if you will. But that's expensive, right? Does that make sense? You can start first axis in the first cycle, next axis in the next cycle in the next port, next axis in the next cycle in the next port. So you can actually sustain 16 accesses at any given time. Actually, you really need to sustain 11 accesses, right? Because you can use the next port at the end of the 11th cycle. Well, this is an expensive way of building a memory that we can access in parallel for different elements. This is called multiporting. So what Cray did was to bank the memory. Basically, you have different banks and addresses. Consecutive words are mapped to consecutive banks in memory. So what you can do is the first word you can access from bank 0 and start that access in cycle 0. The next word which you want to access, you can access it from bank 1 and start that access independently, right? Because it goes to a different structure, different memory bank, if you will. This is the idea of banking or interleaving. What we have done is basically we have interleaved the words across different banks so that we can get the first word from the first structure, the second word from the second structure, the third word from the third structure, and so on. Yes?
How do you store it in different banks when you actually store the vector? How do you store it in separate banks?
So it's the same thing, right? You store the first word in the first bank. You store the second word in the second bank. Third word in the third bank. Again, vector store operations pipelined. In consecutive cycles, you store to consecutive locations. If your memory access took one cycle, you didn't need 16 banks, right? Because you could store or load the first word from that one cycle access memory, and the next cycle you could use the same structure. But because memory access takes 11 cycles, you need to have enough banks to be able to sustain one load or one store per cycle. Okay? And you cannot have 11 banks. Or can you have 11 banks? Ideally, you would want 11 banks, right? The problem is, how do you address 11 banks? We're a binary computer. So 11 banks would have worked, but because you cannot address 11 banks with a binary computer, or you need to have a really sophisticated indexing function to do that, we had 16 banks. You don't want to have 8 banks, because then you cannot start, you can only sustain 8 accesses in parallel. Right? Okay, so this is important to understand. Okay, so if you think of a vector memory system, it looks like this basically. You have 16 banks here, this is like Cray, and you have a base register. If you're doing a vector load, for example, you have a base register, and in consecutive cycles, the stride is added to the base register, and you generate an access to the memory bank, to the memory. And of course, you have a vector length, which is not shown here. In consecutive cycles, you keep adding the base to the stride, and you increment the base also to generate the addresses in the next cycle. And you stop it when you reach the vector length. You do it vector length number of times. So hopefully it's clear to you that if consecutive words are laid out in memory in consecutive banks, with a stride of 1, you can do 16 accesses in parallel. But what if your stride was 16? You have a vector load instruction. You want to load from address A into vector register 1, let's say. And your stride is, somebody set your stride to 16, because it so happens that the vector's elements are 16 words apart from each other in memory. I guess 0 through 15, that's 16, yeah. Anyway. Oh, 16, right? It has to be 16. 32. Dot, dot, dot. You have this banked structure. Consecutive words are in consecutive banks, and your stride is 16. What happens?
You have to solve for the rest of the 10 cycles.
Exactly. So every access goes to bank 0, right? Because your words are laid out in memory such that, let's say these are your banks. Your words are interleaved such that 0th word is here, 1st here, 2nd here, 3rd, 4th, 5th, 6th, 15th here. And now you wrap 16th word is here, 17th word is here, 18th word is here, 31st here, and then 32nd is here. So all of your accesses now go to this same bank. This is called a bank conflict. Which means that you cannot sustain the 1 word per cycle throughput that you need from the memory system. So it's very important what your stride is, and how many banks you have really determines how much memory throughput you get from the system. If it turns out that your consecutive elements map to the same bank, then you have 11 cycles stall between each element. So you're not really getting the parallelism you want. Even though all of the operations that you're going to do on those elements are independent, just because they're mapped to the same location in memory, and you need to access them one by one, and memory takes more than n cycles, more than 1 cycle, means that your throughput is reduced. So that's why it's very important to provide enough memory bandwidth. So how can you solve this problem? Well, what you can do is you can add more banks, right? You can add 1,000,000 banks, and that reduces the probability of two words mapping to the same location. So that's why these machines had expensive memory systems. This was a very expensive memory system for 1970s. Today, it's in all of the memory systems, as we will see in the memory lectures. So so basically, you don't have a problem if your stride is relatively prime with the number of banks. Then your consecutive accesses go to different locations. But if your stride is a multiple of the number of your banks, then you have a lot of bank conflicts. If you're not relatively prime, if you will. So another way of doing this is actually having a prime number of banks. That reduces the bank conflicts quite a bit. But that's, again, how do you index into that, right? How do you map the data? Okay, this is some food for thought for you. People have actually devised mechanisms that randomized the mapping between a physical address and its location in the banks to reduce the bank conflicts also. Okay, so let's take a look at an example. I've given you kind of the basics to actually build a vector processor. Why is this beneficial? Let's take a look at this simple example, the addition of two vectors. And just to make it a little bit difficult, I divided the sum by 2. And we want to add two vectors of 50 elements. This is a scalar code, and these are the assumptions that I'll make for the latencies, if you will. Well, you certainly need to set up the loop iteration count, and we set R1, R2, R3 as the starting addresses of the 3 vectors, if you will. And we're going to add A to B divided by 2 and store the result in C. So in scalar code, you do this in a loop, right? Simple. Basically, you load the first vector, first element of the first vector in the first iteration, first element of the second vector in the first iteration, and you add them, you shift the result, stored in R7, and you store the result in the first element of vector C, if you will. And here we made life a little bit easier by using auto-increment addressing. Remember auto-increment? Because our stride is 1, we can simply increment the address, and we don't need a separate instruction for that. And then we check whether we've finished the loop iterations. If not, we go back and do the same thing for the second element, and then for the third element, and the fourth element, until we do everything for the 50 elements, if you will. So assuming these are the latencies, how many instructions we execute to do this? If you write scalar code, if you do the calculation, you have 4 instructions here. 1, 2, 3, 4, 5, 6. 6 times 50, 304 instructions. So I would argue that this is very inefficient. We will do this in 7 instructions later in a vector processor. So you need to, for each of these elements, you need to fetch the loads, you need to decode the loads, you need to fetch the add, shift, store, decrement, and branch if not 0. And you need to have all that control overhead for each element. So let's remember this number, 304. Execution time, if you have an in-order processor with a single bank, this is your execution time. Basically, it's simple. First 2 loads in the loop cannot be pipelined. So what? Because you have a single bank. So you have 4 cycles to execute these. 11, 22, 33, 37, 39, 40 cycles to execute the entire loop because everything is serialized. So 2,000 cycles, 2,004 cycles for the entire loop. If you actually can have 16 banks, so banking actually helps in order processors as well, right? You can actually overlap the first 2 loads, right? Because these are really independent loads, right? They're accessing different locations in memory, and they don't have any register dependence on each other, which means that you can execute them independently, which means that you overlap their latency. You can start the first load in the at the end of the 4th cycle. So first load starts, so your execution time 1, 2, 3, 4, the first 4 instructions. And then you can start the first load. In the next cycle, you can start the next load because you have 16 banks and these are consecutive words, which means that you can overlap the latency of these 2 loads. Okay. So these 2 loads together, if you will, take 1 and 11, 12 cycles. Right? So if you do that, how many cycles does the loop take? 1, 11, 12, 16, 27, 30 cycles, right? So you'll have 1,504 cycles. So let's see what a vector processor does. Why 16 banks? We already talked about this. You can read this on your own. Okay, this loop that we've seen, which I've copied here, is a vectorizable loop. What is a vectorizable loop? basically, if each iteration of the loop is independent of every other iteration, that loop is vectorizable. You can execute it as a vector instruction, if you want. Not all loops are vectorizable. For example, if this bi was bi plus 1, would that be vectorizable? I guess it would be. But what if you were writing to bi plus 1 here? So your destination was bi plus 1. Then that's not vectorizable because the next iteration is dependent on the previous iteration. So you cannot use a vector crosser for every loop, but for this kind of loop you can use a vector crosser. So vectorized loop, this is the vector code for the same loop. Basically we need to set up the length of the vector, in this case 50, and we need to set up the stride, in this case 1. And the first operation, we load vector A into vector register 0, vector B into vector register 1. We add the two vectors, and we shift the result, and write the result in vector 3, and we store vector 3 in the memory location, starting at memory location C. And these are the number of cycles each instruction takes. Well, first one cycle to do the moves. Here, you have 11 cycles to start the first access, and because we have 16 memory banks, we can start consecutive accesses in consecutive cycles. So we can do, basically, it takes 11 plus 50 minus 1 seconds, right? So you start the first access here, and then next access in the next cycle, next access in the next cycle. So essentially, you have vector length number of accesses, and the first one takes 11, and you finish every access 49 more accesses. You finish the first access at the end of the 11th cycle, and after 49 cycles, you finish all of the other accesses. Okay? So that's how you can compute this. Okay, before we go into how we can optimize this, if you look at this, this takes 7 dynamic instructions. Right? There's no looping here. So 304 dynamic instructions gets reduced to 7 dynamic instructions. You can save significant power. Because of just instruction control logic. You amortize the control of instruction fetch and decode. Okay, so let's see how long it takes. Let's assume one memory port, one address generator, if you will, and 16 memory banks that we assumed before. And let's assume there is no forwarding. Forwarding, I will introduce you to forwarding in vector processors, there's no chaining. And I'll get back to this. Basically, this is the number of cycles this vector takes, 285 cycles. Why? Basically, you need to finish this operation before you start the next operation because you have only one port to memory, one address generator, if you will. You can optimize this a little bit, but that's okay. Basically, this is what happens. The vector operation, this vector operation, finishes the first element after 11 cycles, and then each consecutive cycle, memory outputs consecutive elements because you have 16 banks. The next load, again, the first element comes after 11 cycles, and then after each consecutive cycle, memory outputs the remaining 49 elements. Now you have both vectors in registers vector 0 and vector 1 registers. Now you can do the add. The first add on the first element completes after the 4th cycle, and remember we're pipelined. We have a pipelined adder, so the remaining elements, the remaining sums, if you will, of the remaining elements, each of them finishes in consecutive cycles, so 49 cycles. And you can do the same thing for shift and store. So if you do the calculation of this, it takes 285 cycles. And we haven't really optimized anything yet. You can really with simple changes to the memory system, you can start this load a little bit earlier. But you can think about that. So what was the number for the scaling execution? 1504. Right? We're already at 285, which is more than 5 times faster. So we can do even better, actually, by observing that. So here, we did not start the add. If you look here, we're doing the first element of vector 0 plus vector 1 right here. But there's no reason to start it right here because we have the data of the first element of vector 0 and the first element of vector 1 available right here. Right? We've already fetched first element of vector 0 at the end of the 11th cycle here, and we fetched the first element of vector 1 right here. We don't need to wait for the entire vector to come to start the first addition of the first elements. So all we need to do is to supply this to the add functional unit. So that way we can start the add right here. Yes?
How wide is the vector?
How wide is the vector?
Yeah, like how many elements are you computing at one time?
What do you mean?
Like is it like, because this thing is saying, it's saying that like as if all the adds are happening in one step and then all the shifts are happening and all the stores are happening.
So here what's happening is, so your add is pipeline, right? An add takes 4 cycles. You have a single adder, and you have a 4-cycle pipeline, if you will, which means that you can do only one add. Addition of vector 0, 0th element, and vector 0, vector 1, 0th element. In the next cycle, you can do the addition of the second element 1 of each vector. Make sense? That's why you do the addition for the first element, and you get the result at the end of the 4th cycle here, and then you get the result out of the adder for every consecutive element.
But shouldn't it go add shift store instead of a lot of adds and a lot of shifts?
Add shift store.
Yeah, because it's.
Why would it?
Because you're running it in a loop, right?
It's not a loop. That's the point. We don't have a loop anymore, right? It's a single instruction. It says.
Okay. So
it says add these elements of the 2 vector and store the result into vector 2, and you're going to do 50 of them, and then move on to vector shift.
So it's able to do 50 at one time.
That's right.
Okay.
Exactly. Not at one cycle, but at one time. You have to complete that instruction to move to the next instruction. Okay? But we're going to now we're going to do something like what you suggest. Basically, there's no reason to start this add here. You can start this add right here, right? Because you have both of the first elements of the vectors available at this time. And there's no reason to start the shift until you finish all of the elements. You can start the shift of the first element right here, right? Once the add is complete. And there's no reason to start the store at the end of the shift. It's really, you can start the store once the shift of the first element is complete. So this is called chaining, essentially, which is forwarding. Right? Yes?
Conversely, could we also like in the floating values of memory, could we do like the first 2 elements and then start doing the rest of it?
We'll get to that. Yes. Yes. But then you need something else in memory.
Yeah.
Multiple ports, basically. But we'll get to that. Yes. Yes?
I have a question about the basic coding. So it seems to me that you would always have multiples of 11 for the amount of time that it takes to read values. Like, it seems to me that if you had 11 cycles, that would give you 16 elements to be able to do. That would give you 32 elements. So I don't see how you just add 11 plus.
So one of the banks takes 11 cycles, right? The bank itself takes 11 cycles to access. So if the next access goes to the next bank, you can start that access in the next cycle. Okay? Think about it. Yes?
Also, because so you said there's 62 banks, right? So what? There's 49 elements. Why isn't it like 49 divided by 16?
Say it again?
Why isn't it 49 divided by 16 axes? Or is it because of that? The stride is.
Yes, stride is 1, right? So you have 16 banks. 4, 5, 6, 7. I guess I'll do this. So in your first access, you want to load the first element. So you can start that access in cycle 0. Let's say cycle 0. This is going to take 11 cycles, right? This is cycle 11. The next access, next element is in the second bank. So you can start that in cycle 1, right? It's going to take, again, 11 cycles and finish at 12. The next access is to this, 2. you can start that in cycle 2, right? And again, it's going to take 11 cycles. So it's going to finish at cycle 13. So if you think about this, if you're going to load 50 of them, the next access, you can start in cycle 3, next access 4, 5, 6. I guess this is 15. And the 16th element, well, it's also here. You can start in the 16th cycle because this bank is already done servicing the first one. Make sense? That's why what I drew was the first element takes 11 cycles, and then each consecutive cycle, you can actually get one element per cycle from memory because you already pipelined, if you will, you already accessed different banks. Yes?
So I guess my question is, why do we have to start the second one at time 1? Like, why can't they just start all the things at once and then just get time?
Oh, okay. So, yeah, you could if you had different addresses. If you can supply the addresses in parallel to these banks, yes, you could do that. But the assumption is that you have only a single address bus going to memory. That's okay. I did not give you that assumption, but you could definitely add more hardware cost to this, and you could do all of these in parallel. Also. That's in a sense that's like having multiple memories. Okay. Yes.
So we could start the second cycle as such at the 12th time position as well.
You could start the what? Second.
The second element access. Instead of accessing the 16th element, the 16th cycle, 15th cycle, start at 12th as well.
That's true, but you need to still. You could start the 6th, but you need to load the other elements also, right? You cannot just skip to 16. You have some things in between. Okay. So vector chaining is essentially data forwarding from one vector function unit to another, and you've already seen this, right? It's simple. You have a load unit, and you're loading a vector, and each element comes in consecutive cycles. So instead of loading the entire register, why don't we, when we get the first element of the vector, why don't we forward it to the multiplier in this case? And when we get the first result out of the multiplier, why don't we forward it to the adder? That way you don't need the entire register to be loaded. Once your element is ready, you can forward. It's very simple. It's the idea of forwarding. It's called chaining. So if you do this, I guess you remember the code here. This is the first vector load. This is the second vector load. This is the vector add. Now we can start this add right after both of the elements both of the first elements of the vectors are ready. You can start the shift right here, and actually here, ideally you could start the store here, but this load is still going on, and we assumed one address generator to memory. So you have to start the store at the end of this load here. You could have started earlier. So you go down to 182 cycles with chaining. Now, let's get back to your question. These two loads, we didn't really pipeline them. Why? Well, because we didn't have two address generators, two ports to the memory, if you will. So if we have two load ports, and I already told you why you cannot pipeline these two, this load and this store, if you will, because, again, we have one address generator, one port to the memory. Now, if we add, each memory bank is a single port. So you bottleneck by your memory bandwidth. If you actually add two load ports and one store port, you can completely pipeline pretty much everything here. Now the first load, you can start here. The second load, you can start one cycle later. Because now you can do two accesses to this bank. One access, the next access. And you can get zeroth elements for vector 0, I guess it was called A. And you can also get zeroth elements for the second vector, B, at the same time. And you can do the store in parallel with the load here. Now, it looks like you already overlapped the latency, so maybe you don't need this parallelism, but I cannot see. So we go down to 79 cycles. Remember that what it was for scalar execution was 1504, right? So you get almost a 20x speed up with the vector processing. Of course, you need to add more memory bandwidth. So now you see why memory bandwidth is important in vector processors. Right? Okay. I guess we'll keep moving on. Some questions for you. What if number of data elements is greater than the elements in a vector register? So here, we assume that your vector width in the machine is greater than 50. Let's say 64, which was crazy width. What if you have more data elements? What if your vector elements are, you're adding 2 million element vectors, but your hardware can support only a vector length of 64? Well, need to break the loops in that case, so that each iteration operates on number of elements in a vector register, right? So your vector register, obviously you're not going to have 1 million entries in your vector register, right? Otherwise that'll be an expensive machine. So how do you break the loops? If you have 527 data elements in this example and 64 element vector registers, you have 8 iterations where vector length is 64, and you have one final iteration where you need to change the vector length to 15 when you're programming this. This is called vector strip mining, if you will. You basically divide the loop iterations with your vector length. So this change of vector length is important, right? You cannot have longer vectors than your data elements. Okay, what if your vector data is not stored in a strided fashion in memory? Let's try to make this a little bit more general purpose. What if your matrix was a sparse matrix, for example? You had a lot of zeros and you don't want to store the zeros. Well, a lot of vector processors use indirection to combine elements into vector registers. These are called scatter-gather operations, so let's see what they are. Let's say you want to vectorize a loop like this with an indirect access. Here, your address is not simply a function of your loop index, but really a function of indirect array. And this is how you can store a sparse matrix. Like you can say, actually, I should have an example of this. Actually, let me go through this. Basically, there's a gather instruction. What it does is you can load indirects from this C base. You really want to add the index that's coming out of the D array into the base address of the C. And there's a load indirect instruction that accomplishes this. This is really a gather, and we will see how that operates right now. Basically, these are implemented in hardware. You essentially have an index vector, which is added to the base register to generate the addresses. So if you look at this, you can think of this as your D array. This is your index vector, and this is your data vector, if you will, that you want to get out of the memory. What happens is you have hardware support that adds the base register to the index to get these different locations in memory. Does that make sense? I went through this relatively fast, but you could think of it. It's relatively simple. You're basically, I don't want to go back to that adder, but remember, you have this adder that generated the address. You had this base register that took the stride here. Well, in this case, you really get your index from a register, if you want. In this case, your register will be specified by the vector register D. So for each element, that's what you generate. Okay? Make sense? Okay, so you can do this kind of operations in a vector machine. Basically, you can gather the data that's, if you will, scattered around in memory. This is your memory layout, if you will. You can take the data that's not zero, that's specified by this index vector, by supplying an index register that gives you the indices of the elements that are not zero. Of course, you need hardware support for this, so you don't have stride anymore here, right? This is called a gather operation. Similarly, you can do the stores that way. Okay. Actually, you can think of this as the stores also. you have this index vector, and this is the data you generated in a vector register. Now you want to store this data in memory in a sparse matrix. You want to store the first element in location 1. You want to store the second element in location 3. You want to store the third element in location 7. And you want to store the fourth element in location 8. So you do an index store. That's called a scat. Scatter is a store, gather is a load. Okay, let's take a look at the conditional operations. What if some operations should not be executed on a vector based on a dynamically determined condition, which is the interesting part, right? So let's make the loop a little bit tougher, if you will. So if AI is not equal to 0, then you do this. Otherwise, I guess BI stays the same. So how do you actually vectorize this loop? Basically, you can use math operations. And I told you what the vector mask is, right? It's a register. It's a bit mask determining which data element should be acted upon by the instruction, by the operation. So if you want to code this, you set the vector mask bits based on the condition. If the vector register 0 is not equal to 0. Just test each element of the vector register and set the mask for each of the vector elements. And this multiply later on is essentially multiplying A and B, if you will, which are stored in vector register 0 and 1. It multiplies those elements whose mask bit is not set to 0. Make sense? Okay. Well, I guess I should have asked you earlier, but this is essentially predicate execution, right? Your mask is really the predicate, and this multiply is really a predicated multiply. Each element is predicated. Each operation that the multiply does is predicated upon the mask bit. In fact, vector computers are the first computers that implemented predicate execution. This was in Cray 1. Cray 1 had these mask registers. Okay. Well, you could do even more complicated things. You could actually, I'm not going to go through this, but if you have an if then else, what you can do is actually you can complement the mask, right? You do the if part first, and to do the else, you complement the mask and you do whatever operation specified is there. Okay? So this is actually how GPUs operate, as we will hopefully see if we get to it. Except the programmer doesn't need to do this. So the difference between today's GPUs and old-time vector machines is programmer doesn't need to deal with these mask registers in today's GPUs. They're easier to program. The programmer programs in a similar way as you would do in a C program, for example. You don't need to vectorize your code. You just need to make sure that your threads, if you will, operate on different data elements. And you can code like this exactly. You don't need to convert the code to vector loads, vector stores, vector masks. A GPU converts this code dynamically, if you will, assuming the different threads operate on different data elements, to this. This is all done in hardware, in GPUs. Okay? Mask vector instructions, how do you actually implement them? Well, this is essentially, you basically check the mask bits to enable the writes to the vector register. Right? So in addition to the data elements coming into your adder, you also have mask bits. And the mask bits basically enable your destination register. This is one implementation. It's inefficient because what if a lot of your mask bits are 0? Then you're doing a lot of these adds for no reason, to just drop them in the end. So people have come up with better ways of implementing this. This is called a density time implementation. So you have some hardware that scans the mask vector first and executes only those operations with non-zero masks. It complicates the hardware a little bit, but it's a lot more efficient. Okay, so some issues. We already talked about this, so I'm not going into this. Trident banking, as long as these are relatively prime, then you can have access in parallel. Storage of matrix, we already talked about this also. This is just for your benefit. What is row major? What is column major? Are you guys familiar with those concepts before? From 213? Okay. Okay, then you can answer any question about it, huh? There's some dissonance in those two answers. You're familiar, but you cannot answer questions. Alright. Basically, you need to change the stride when accessing a row versus column, because you cannot store the same matrix in both row major and column major order. And this is some drawing that I gave you, just so that you have it here. So, to wrap up, at least the classical vector processing, let's revisit array versus vector processors. As I told you before, array versus vector processors are really a purist distinction. Modern SIMD, single instruction multiple data processors, are a combination of both. And, well, just to remind you, but if you look at a vector instruction, this is the vector processor, pure vector processor form. But what happens is really you have multiple adders in an existing vector processor. So what happens is you do multiple adds at the same time, like an array processor, and you also pipeline the adds. Does this make sense? So basically you have the addition of zeroth elements, first elements, second elements, and third elements going in parallel, and you also pipeline the remaining elements. So fourth element, fifth element, sixth element, seventh element are pipelined behind that zeroth, first, second, and third element, but they also happen in parallel. So you can do multiple adds in parallel and also multiple adds pipelined, if you will. It's a two-dimensional thing. And if you look at a vector units, you have the vector registers formed like this, and vector registers feed different execution units like this. So in a sense, you have partitioned vector registers, because you can only feed some functional units from some partition of the vector register. It simplifies the design quite a bit. Okay? This is called a vector length. So if you look at an existing vector, I'm not going to call it a vector processor anymore, SIMD processor. If you want to be a purist, this is not a vector processor anymore. You have multiple units that you can operate in parallel. And let's say you do a load, and your vector length is 1, 2, 3, 4, I guess 32 in this case, right? This is how the load happens. If load your width, if you will, SIMD width is 8, and you pipeline 4 of those 8 operations, so you can do 32 operations in 4 cycles. That's how the load happens. In the next cycle, you can actually start to multiply, and your vector length is again 32, and it's divided into 4 cycles. And then you can also start the add in the next cycle. So at any given point in time, you're doing 24 operations per cycle, and these are different operations, if you will, at different units. And you can start the next load once the first load ends. You can start the next multiply once the first multiply ends. And you can start the next add once the first add ends. Okay? So this is vector and array processor combined together. Okay. So you might be thinking, can you actually automatically vectorize the code? And people have banged their heads on this for a long time. And if your loop is vectorizable, you could actually automatically parallelize a lot of this. Of course, the compiler needs to do analyses to make sure that there is no overlap between the arrays, right? So if you want to vectorize this, you need to ensure that the loop iterations are independent. Now, what does that mean? You need to ensure that these arrays do not overlap for the given n you have here, right? Because if they overlap, then your loop iterations are not independent anymore. Or at least C doesn't overlap with A and B. A and B could overlap, I guess, right, in this case. Because you're not writing to A or B. Okay, so if you look at this, let's assume that they are independent here. The sequential code would execute like this. Iteration 1, iteration 2, iteration 3, iteration 4, ... They're all independent. What you could do is the compiler can figure this out, and the compiler can vectorize each of the instructions, right? Loads, adds, stores. Now we have compiler forms a vector instruction consisting of data elements from different iterations. So remember this picture. Well, it's essentially a compile time reordering of sequencing of operations, right? Instead of doing sequential operations, you actually move the iterations so that they happen in parallel. Of course, the key is this loop dependence analysis, and it's not always easy to do. Especially if your programs are, if you have pointers, for example, in your programs, that you don't know where they will write. Okay, so remember this example, because what's happening here is you have independent loop iterations and that are being executed in parallel in a vector fashion. So in a GPU, we will see that what you do is you just write this kernel just like you're writing sequential code. And what the GPU does is GPU dynamically executes these different kernels at the same time in a SIMD fashion. Meaning it aligns these loads together from different threads, because threads are executing the same code. They're all executing different iterations of the same loop. Okay, we'll get to that soon. Okay, vector machines, they're good at exploiting regular data level parallelism. Hopefully you're convinced of that by now. Well, we've covered a lot of these. They simplify design, they improve performance, and the reason is because you can do the same operation on multiple elements. The problem is performance improvement is limited by the vectorizability of the code, and scalar operations, as I showed you in one of these boards here, limits your performance, and you can actually, hopefully you're able to do calculations. If the parallel portion of your program, if the vectorizable portion of your program is 50%, with a vector machine, you can only get 2x performance benefit, right? But hopefully that's more than 50% in some applications like graphics. Hopefully most of what you're doing is here. But still you're limited by the sequential bottleneck. If your vectorizability, if you will, is 99%, if your program is 99% vectorizable, again, the maximum speed up you can get is 100. Right? So you have to do something about the scalar portion. That's why Crayon was the fastest scalar machine. So many existing sequential ISAs also include SIMD operations, if you will. So this is not limited to a machine that's all doing vector processor and you add scalar processing to it. Many existing scalar ISAs include vector-like operations. And you may have heard of some of these. ARM has advanced SIMD, for example. Intel has MMX, right now SSE. Probably they're coming up with some other acronym that has two of the same letters first and then something else next. So let's take a look at these very quickly. The idea, this is the Pentium MMX operation. This is one of the first ISAs that introduced array-level parallelism, if you will. And this is a very good paper to look at if you're interested in learning about these. So basically, the idea was to have one instruction operate on multiple data elements simultaneously. It's array processing, yet much more limited than what I described before. Why much more limited? Because you don't have a vector length register. And your opcode determines your data type. And the reason was the reason Intel designed this was because they figured out multimedia operations are very common in the processors, in the code that's being executed on their processors. So if they speed these up with something that the programmer can use easily, they can get significant benefit. So what they did was they specified multiple operations. In this case, you could, this is a 64-bit register, and you could treat this as 8-bit bytes, and you could do 8 adds on those 8-bit bytes. Or you could treat this as 4 16-bit words, or you could treat these as 2 32-bit double words, and you could do 2 additions here, if you will. You could add 2 of these registers and do 2 32-bit double word adds. Or you could treat this as a scalar register, if you will. In a sense, this is poor man's vector that's added to a scalar ISA. You're partitioning your scalar register into pieces, and the pieces are operated on in parallel. And stride is always equal to 1 in their mechanism. So one example, I'll go through this relatively quickly. This is again from that paper. Let's say you want to overlay 2 images. You have this image. You want to, and this is supposed to be blue. The background of this lady is blue. What you want to do is, well, you cannot tell this from this picture. And this is supposed to be a tree or something like that. Basically, what we want to do is to replace all of these blue elements in this image, blue pixels, with this background image. But we don't want to lose the lady. So our goal is this. So how can you do this? Basically, you can chop this image up to each 8. Well, I guess 1, 2, 3, 4, 5, 6, 7, 8. So one pixel is 8 bits, and you can store 8 pixels in one register. And you can do this in a parallel fashion, where you can operate. You can do the same operation on 8 pixels at the same time. So what do? Basically, this Intel MMX provides a packed compare equal byte instruction, which basically takes one 64-bit, let's say 8 pixels from this image, and 8 pixels from this image, if you will. Well, what we want to do first is figure out whether these are all blue. So we take 8 pixels from this image and compare those 8 pixels with all blues. And the result of this instruction, 8 pixels from this image go into multimedia register 3, and we have blues going into multimedia register 1. And what this instruction does is it compares the 2 registers in a SIMD fashion. Each 8-bit element is compared separately. So what the instruction does is this byte equal to blue? 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 For all 8 bytes. And the result is, if the byte is equal to blue, you get 0, you get all 1s. If the byte is equal to 0, is not equal to blue, you get all 0s. So that's the result of the instruction. This is an array operation, right? This is a vector operation. And you can think of the remaining parts of the program. I will not go into it in detail, but what you do is, for those locations that you determine to be blue, you set the destination pixels of the image from this image, and for those locations that you determined are not blue, you set the destination image pixels from this image. Basically, if and else, right? So this ISA also provide pack and pack and not operations, if you will. And then you can set the image and you can OR the values in a register to get the final image. So the final code is something like this, basically for an 8 pixels. And then you need to do a loop, of course, over this because there's so many. You don't have only 8 pixels in your image. So it's fun to go through some of this code. This is essentially vector code, if you will. Not in a different way, in a much more limiting way. Okay. Any questions so far? Am I going too fast? Too slow? No? Neither? Okay. No, I wanted to cover VLIW today too, but let's see. So graphics processing units, as I told you, these are SIMD machines, except they're not exposed to the programmer. That's the way I like to think about them. If you look at a shader core, I'm not going to general system architecture. We can have a course on these actually. But if you look at one of the cores, what happens is you have these scalar pipelines that are controlled by a SIMD unit. They all do the same operation at a given cycle. That's the idea. Except the programmer doesn't write the code in a SIMD fashion. They write the code as threads, if you will. Except these threads that are being executed in these pipelines, they all do the same operations. They all execute the same kernel, if you will. Remember that picture? I'll flash it to you again. What the hardware does is you basically have the same program counter that fetches the same instructions and distributes it to these different pipelines, and they all operate on the different elements. All the programmer needs to do is basically ensure that threads operate on different data elements. They don't need to rewrite the code. Okay, so this is called SIMT, if you will, single instruction multiple thread by NVIDIA. And what you have is, you have a set of threads that execute the same instruction on different data elements. but the program is written as threads. And this is called a thread warp, if you will. And a thread warp has a common PC. Each of the threads operates on different data elements, and they're fed to the SIMD pipeline. Basically, all threads run the same kernel. And if you want to know what a warp is, why they call it a warp, the threads that run lengthwise in a woven fabric is apparently called a warp. So these threads do different operations. Actually, let me get back to this. Essentially, these threads do different operations over time, but they do the same operation on different data elements at the same time. So the programmer needs to supply this, and the hardware executes different threads in parallel with a single instruction, multiple data fashion. Okay, does that make sense? As long as the threads are like this, if you will, they're executing the same instructions on different data elements, this works. And as long as they're the same code, if you will. Okay, so how do you access the data? Well, basically, same instruction, different threads, uses thread ID to index and access different data elements. And this is just a picture to show you. But if you look at the code that you would write in a GPU, it looks something like this. This is your CPU code of adding two arrays, and GPU code is very similar. There are, of course, some details depending on how you manage things, and I'm not going to go into those, but essentially you're adding two arrays. There is no SIMD code here, right? And you can look at it in more detail. I guess I'll skip this. Yeah, I'll skip that because you don't really need to think about that at this point. So what's the difference, basically? What's the difference between traditional SIMD and an existing GPU, if you will, warp-based SIMD? And remember, warp is a set of threads that execute the same instruction on different data elements. The difference is, really, traditional SIMD contains a single thread. Right? Remember, we had the vector load, vector store, vector add, vector shift. You really have a single thread there. Programming model is really SIMD. There's no threads. And software needs to know the vector length, if you will. The programmer needs to deal with the vector length in that case. And ISA contains vector and SIMD instructions. Whereas warp-based SIMD consists of multiple scalar threads executing in a SIMD manner. Basically, the same instructions executed by all threads, but the programming model is really different. It does not have to be lockstep, right? Meaning you don't finish one instruction to go to the next instruction. And each thread can be treated individually. Now this gives you some opportunity to do optimization, both at the hardware and software layers. You can actually take a thread and place it to a different warp. And software doesn't need to know the vector length as well. And this enables some memory and branch latency tolerance that I will not go into. And ISA is actually scalar. This is one key distinction. Your ISA is really scalar. I'll get to it. Vector instructions are, what's happening is vector instructions are being formed dynamically. Yes?
So if it's not lockstep, then does that mean that you're fetching different instructions for each one? And if so, then does that get rid of the benefits of having the significant where you only have to fetch things less times?
No, it's not lockstep in the single thread. So you can move the threads around, basically. You're still fetching the same instruction from different threads. So the fetch is still lockstep. But let's say one thread is stalled for some reason. Here, if one instruction is stalled in SIMD, in the traditional SIMD, if one instruction is stalled because for some reason it gets to a memory bank conflict, you have a problem, right? Because you cannot move to the next instruction. Whereas, actually, maybe I'll get back to this previous picture. What happens in a GPU is you have a thread warp, and let's say one of them gets a long latency cache miss and gets stalled. What you could do is you could switch to another thread warp. And that's how GPUs actually tolerate memory latency. This is the idea of fine-grained multi-threading, right? What they do is they fetch from different thread warps in consecutive cycles, And if one of them gets a cache miss, they basically get out of the way, if you will, and other thread warps can continue executing. Whereas in a SIMD programming model, it's difficult to do because you have a single thread. Yes?
So it's not lockstep between warps, but it's lockstep within the warp?
So that's a very good question also. It's lockstep within the warp, but again, because these are threads, what you could do is you could try to, once you figure out what are the stalled thread warps, you could have hardware that analyzes these and try to regroup warps. You could put those things that are stalled together, and you could take out the thread. So think about this. Let's say you're doing a load instruction. You're doing the same load instruction in the same thread warp 6. Only one of them missed the cache. You don't really need to stall that one of them. What you could do is you could have additional bookkeeping that just removes this, puts it in a different warp, and places some other thread that is executing the same instruction into this warp.
So is that all handled? Is like the scheduling of that all handled by the hardware, or is
that's right?
Software?
Yeah, like at least this level of scheduling is handled by the hardware. And existing GPU hardware does things like this, basically. If one of the threads in a warp is stalled, why don't we regroup the threads in different warps such that we can continue execution fast?
But aren't all the threads in a warp using the same PC?
Yes.
So then, like, if another thread in a different warp is a different PC, it can't be moved.
Yeah, you cannot do that, right? You have to find a thread warp with the same PC. But because these are different threads, you could do it. Well, assuming there is one thread warp with at the same PC, of course. Okay? So this decoupling of the programming model and the hardware model, if you will, helps optimize a lot of these things. Because we're not limited to vector instructions and lockstep anymore. So I guess I'll introduce another term at you today. Basically, if you think of this, this is really SPMD programming model, or single program, multiple data programming model implemented on SIMD hardware. So you should probably be familiar with SPMD. This is really a programming model rather than computer organization. You have single procedure that operates on multiple data. It's essentially that different iterations operating on different data elements. Right? If you think of this iteration as a program or procedure, that's your single program. And multiple data elements are the different data elements that are operated on by those different iterations. So you could, basically, in this case, each processing element executes the same procedure, except on different data elements. And you could have procedures that synchronize at certain points in program. In the barriers, for example, that I showed you in the previous lecture. Essentially, you have multiple instruction streams, multiple threads that are executing the same program. And this is a lot more general purpose than SIMD programming model, if you will, where you actually program with vector instructions. Why? Because now each program or procedure can execute a different control flow path. So you could have branches in the code, and they can work on different data at runtime. In fact, many scientific applications are programmed this way. So this programming model can be executed on a multiprocessor. Right? Think about the different loop iterations that I showed you before. They can be done in parallel, but they could be executed in different processors. If you have a multi-core processor, you could execute them on different processors. Right? Well, GPUs don't execute them on different processors. They take advantage of the fact that these are the same threads. And they execute them on a SIMD manner. They take advantage of the fact that these threads would be executing at the same PC at some point in time. And they amortize the cost. So you could think of it that way. Okay. So I'll just give you one problem. So this SPMD, single procedure, multiple data execution on SIMD hardware. Again, I told you that NVIDIA calls a single instruction multiple thread. Now we don't have vector masks, right? Because we don't have a vector instruction. This is the thread the programmer wrote. And there's an if, then else here, right? And there's another if, then else here. So the GPU needs to execute this, right? What might happen is you have different threads, and you group them into a warp starting from this location because they all have the same PC program counter. Thread 1 may go this way. thread 2 may go this way. Thread 3 may go, well, it happens to go the same way as, I guess, thread 1, thread 2. And thread 4 may go this way. And you started with the common PC, but now they're diverging. So what do? Well, what the GPU does is, initially, all warps in the thread execute the same PC. And when you get to a branch, the GPU determines the branch condition for each of these different threads. And some of them will take path A, some of them will take path B. Well, GPU does predicate execution in hardware. It figures out which ones should execute path A, and it executes them first. Only some of them. Masks the other ones out. So all of the threads still execute path A, but based on the branch condition here, the threads that are not supposed to execute path A are masked out, if you will. They don't write. They don't do these operations. And in the next cycle, well, not next cycle, when you reach the merge point, if you will, in this case, let's assume that there is a single instruction, the GPU goes back and executes those threads that are supposed to execute path B. In this case, they're complementary. Right? And when both of the paths merge, the GPU continues executing all of them at the same time. So essentially, this is predicated execution implemented in hardware. Right? Purely in hardware. It's not exposed to the programmer again. You can think of it as vector masking also. The branch condition determines which threads should execute this path versus that path. Okay? So of course this reduces your efficiency in SIMD. So this is just food for thought for you. Well, I don't know what happened here, but food for thought for you. Let's say you had other warps. 1, 2, 3, 4, 5, 6, 7, 8. Let's say you had other warps that are also doing the same thing. You may be able to figure out which ones are actually executing path A and which ones are actually executing path B, and pack different threads together. So some GPUs actually do this optimization in hardware to improve the efficiency of this. So I'll let you think about that. Not in the same unit, right? Yeah. But there could be multiple warps, if you will, that are also doing the same thing. And if they happen to have the same PC, if they happen to have the same program counter that points to path A, you may be able to merge them together. Because these are different threads, right? Okay, so just to give you an example, this is actually an old core, if you will. The NVIDIA GeForce GTX 285. What it has is, if you look at this core, I guess, let's see, 8 units share a single instruction stream decode unit, which means that they all have to do the same instruction, and each has a multiply, add, and multiply unit. And you need to store the register context. Why do you need 64 kilobytes? Basically, you have groups of 32 threads that share the instruction stream, but you can execute only 8 of them in parallel, which means that you have 32 threads. You can do 8 in parallel. You have 4 cycles to finish a warp. Each group is called a warp, and it can have 32 warps simultaneously interleaved in the machine. So if one warp stalls, you can execute on another warp. This fine-grained multi-threading across the warps. Which means that you have 32 threads times 32 warps. You have 1,024 thread contexts. That's a lot of threads. Right? And that needs to be stored in the register file. So GPUs have big register files to store them. And this is actually only one core of a GPU, if you will. This NVIDIA processor has 30 of these things. So you really have 30,720 threads. The interesting thing is, some of them can be executing at different PCs. So you don't have SIMD, if you will, across all of them because you have different program counters in each of them. So the SIMD really happens within this core. Okay? And you can study these things. These are interesting. Yes?
How do you handle nested branches?
How do you handle nested branches? Oh, okay. So you're thinking ahead. Basically the same way. you do another fork, but you just need to provide the hardware to figure out what should be executed and what should be executed next. So there's an algorithm that's designed in GPUs called the stack algorithm, if you will. You basically push on the stack what paths you have not executed yet, and you go back and pop the stack once you get to the merge points.
So does that mean there's like a limit to how many nested branches you have?
That's an excellent question. Actually, the answer is I don't know. But there should be probably. Or there is a way that the GPU... Yeah, I haven't thought about that, but that's a good question. Maybe you can figure out and let me know for the next lecture. Do you guys know? Chris?
No idea.
Okay. Okay, I'm curious now, so we'll have to figure this out. Okay, so now that you know about GPUs, let's quickly cover VLIW before we end. You already know the basic concept here. Basically, we have a very long instruction word, and the instruction word specifies multiple operations, except they're not on the same data. They're really independent instructions packed together by the compiler. So this is a way of exploiting irregular parallelism, because they're not operating on the same data. They can be operating on a totally different piece of data. Basically, packed instructions can be logically unrelated. Contrast this with SIMD. The idea is compiler finds independent instructions and statically schedules or bundles them into a single VLIW instruction. And this is what we've already shown you before. You can have totally different instructions, independent instructions, packed together, but the compiler guarantees that they can be executed in parallel, and they are executed in parallel in the multiple functional units. So you have multiple functional units. Each instruction a bundle is executed in lockstep. That's another property to make life easier for the hardware. So if any instruction stalls here, the whole instruction stalls. Instructions in a bundle are statically aligned to be directly fed into the functional units. Again, the goal is to make hardware simpler. Hardware should not detect dependencies between instructions, and hardware should not figure out which instruction should go to which functional unit. The compiler has visibility into the processing elements in the machine, and this processing element may do only adds, for example, and this processing element may do only multiplies. The compiler aligns the code such that it conforms with the hardware. When the hardware fetches this multiply, it directly goes into the multiply processing element. When the hardware fetches this load, it directly goes into this load processing element. The compiler doesn't put the code such that there's a load element here only, and the load is here. If that was the case, and this is a problem in the superscalar clusters, you need to take the load from its location and route it to the load unit. Right? Think about the reservation stations that we discussed. Right? You need to distribute the instructions to the reservation stations. In VLIW, the compiler does it for you. It has to have visibility into the machine structure, which means that now you're very microarchitecture dependent. Right? You're exposing the microarchitecture to the compiler. So this was introduced by Josh Fisher in the seminal paper, which I recommend you to read. And he also talks about how you could compile into this architecture, and which we're not going to get into. You can take 740 for that. So at the time, he called it the enormously long word instructions. That was the ELI 512 machine that he designed. Instructions were 512 bits, basically. Well, contrast this with. So philosophy is similar to RISC, basically. Remember RISC? Compiler does the hard work to translate high-level language to simple instructions. And hardware does little. It's very simple. Hardware in MIPS, you didn't even want interlocking. The compiler schedules the code, right? Original MIPS. VLIW, the same philosophy. Compiler does the hard work to find the instruction level parallelism, and also hard work to lay out the code such that the machine is simple. Hardware executes each instruction a bundle in lockstep. No need to do dependency checking between instructions and across instructions as well if the compiler knows the latency of each instruction. And that was the philosophy. That was the philosophy in RISC also, which hopefully led to simple and higher frequency, easier to design hardware. And you can get this from this paper, basically. There's one central control unit featuring a single long instruction per cycle. Each long instruction consists of many tightly coupled independent operations. And each operation requires a small, statically predictable number of cycles to execute so that the compiler can schedule the code in the machine, both in the same cycle and both across cycles. And you can read this. This is actually a nice thing to read. So people have actually built these machines. These two were some of the early machines that were not successful. I talked about multi-flow trace. Josh Fisher went on to build these machines, and he actually tried to build a 28-byte machine also. Transmeta Crusoe that we talked about earlier translated x86 code into internal VLIW format. And perhaps the most successful commercial machines are actually digital signal processors and some embedded processors from TI, Trimedia, and ST Microelectronics. Those are all VLIW processors. It's easier to find parallel instructions that can be done in those systems because these are, think about digital signal processing, it's very regular again, right? You can schedule your operations, compiler or the programmer can hand schedule the operations on a pipeline. Intel i64 is a similar machine. It's not fully VLIW, but based on these principles. Basically, they kind of violated these principles. So you can have instruction bundles that have dependent instructions. So the hardware is not as beautiful anymore. The hardware is really beautiful in a VLIW machine, a pure VLIW machine, right? You don't need to do anything, almost. In SIMD also hardware is beautiful, but it exploits a different kind of parallelism. Okay, I'll not go into Intel i64, but you can read it. The key thing I would like to get across is what are the advantages and disadvantages? Well, VLIW, no need for dynamic scheduling hardware, right? You can have, you don't need to do auto-order execution. The compiler lays out all the code. You don't need to do superscalar execution because the compiler ensures that parallel instructions, the bundle instructions in a very long instruction word can be fetched and executed in parallel. Again, no need for, I already told you this. No need for dependency checking, and no need for instruction alignment and distribution to different functional units. Compiler did that for you. Disadvantages, well, here it is. The same thing. Compiler needs to find n independent operations, right? Whenever you want the compiler to find independent operations, if it cannot, what does it do? It inserts no ops into a VLIW instruction. And this leads to loss of parallelism and code size increase. The other thing here is you need to recompile the code. If you're in the next generation of the processor, you change the width of the machine. If you want to fetch 28 instructions per cycle versus, whereas your previous generation fetched 7 instructions per cycle. Then you need to recompile the code. You need to recompile the code if your instruction latencies and functional units change. Or you need to make the hardware more complex. You have one of those choices. And this is unlike hardware-based approaches like superscalar or out-of-order execution. And lockstep execution causes independent operations to stall. No instruction in progress until the longest latency operation within an instruction is done. Any questions? Is this all clear? Hopefully this is a simple concept. I haven't given you the VLIW code, but you can imagine what it is. So to summarize, this simplifies the hardware, but requires complex compiler techniques that we did not go into. And you should take 740 if you want to go into it. They have not been commercially successful in the general purpose computing market, VLIW architectures. The main reasons, well, there are many reasons potentially marketing reasons as well. But the software base was too hard to tackle, if you will. The compilers put too many no-ops. This is the VLIW no-op problem, if you will. Parallelism is hard to discover at the compile time. Static schedule was intimately tied to the microarchitecture. Again, code optimized for one generation performs poorly for next. And there's no tolerance for variable latency operations. Right? If you get a cache miss, you stall the entire machine. You could do out-of-order execution, but now you complicate the hardware. It's not as beautiful anymore. So you lose a lot of the beauty of VLIW if you want to tolerate variable latencies. And again, we go back to the fundamentals that we discussed earlier. How can the compiler figure out whether a load will be a cache miss or a cache hit. Very difficult. The good thing is, most compiler optimizations developed for VLIW are actually employed in optimizing compilers today to enhance performance for superscalar machines or any other machines today. They enable a lot of code optimizations. And this was one of your exam questions also, right? If you actually do reordering with a machine that does interlocking benefit. And the answer was yes, because you could eliminate some stalls, right? So all of those optimizations that were developed to do code reordering actually helps these dynamically scheduled out-of-order superscalar machines also because they reduce stalls. And VLIW has been very successful in embedded markets. So if you buy a digital signal processor today from TI, it's a VLIW processor. Okay, looks like we've gone through all the slides. Oh wow, is it late? No, not yet. Okay, so I will distribute the exams and I'll take questions at the beginning of the next lecture.